Good morning, everyone. My name is Keira Proctor, and I'm the Managing Director of the A. Proctor Group Limited. And welcome to the 10th in our series of webinars. We've been running these regularly since April, and the full series is available on our website at www.proctorgroup.com or on our YouTube channel. Today we're going to take a look at how we design housing with low energy use in mind, and how the principles and guidelines of the Passive House Standards can inform that. While the Passive House Standards themselves provide an excellent framework for low energy design, the strategies they embody can be applied to benefit all housing, regardless of the regulations and assessments applied. So we'll begin today by taking a look at what those principles are and what requirements and standards apply to meet Passive House certification. We'll then move on to consider how these concepts can be applied in a more general context, bringing the benefits of low energy design to all types of projects. The Passive House framework originated in the late 1980s, with ideas developed by Bo Adamsson of Lund University, Sweden, and Dr. Wolfgang Feist of the German Institute for Housing and the Environment. These research projects led to the construction of several experimental homes in the German city of Darmstadt. Building on these early 90s experiments, Dr. Feist founded the Passive House Institute in 1996, with the aim of developing and refining this concept and ultimately promoting its use around the world. From the first projects outside of Germany in the early 2000s, Passive House certified buildings can now be found all over the world. The actual standard itself, however, only codifies a set of principles that have been applied to buildings for a considerably longer time, even back as far as the Middle Ages, albeit in a far less refined form. As building regulations have developed and energy performance has become a more important consideration, elements from the passive principles have become more and more integrated into modern homes and are increasing beyond high-end self-build to be part of mainstream housing practice. There are 5 basic passive principles: thermal insulation, thermal bridge free design, airtightness, ventilation with heat recovery, and passive house windows, or more generic, high-performance glazing. The purpose of designing according to these principles is to minimise the energy inputs required to maintain a comfortable indoor temperature. Ideally, the space heating and cooling energy requirements can be reduced to the point that passive sources such as solar gain and heat from the building occupants are sufficient for the most of the time. The Passive House Institute provides software, known as the Passive House Planning Package, or PHPP, to calculate these energy loads, and provides prescriptive guidance and details along with product certification. While this approach certainly simplifies the process and ensures rigorous adherence to good or best practice, it does not always allow designers the necessary flexibility to balance the full range project requirements. In such case, the Passive House guidance and principles can be viewed as best practice recommendations for designing buildings assessed by other means such as national building regulations. That said, the verification and certification services provided by the Passive House Institute can serve to greatly simplify planning and approvals for such buildings and reinforce confidence and trust with subsequent buyers and sellers. So let's now consider how the 5 basic principles can be applied and what they mean. Thermal insulation is what limits the loss of heat from the building envelope and is the cornerstone of the fabric-first approach to building design. This approach seeks to maximise the performance of the basic components of the building, rather than relying on mechanical or electrical systems. The fundamental physical property of insulation material is their thermal conductivity, also known as the K value or lambda value. This property measures how well heat can flow through the material by conduction. In this mode of heat transfer, the heat energy is transferred between the individual molecules of a material by direct contact. Because of this reliance on physical contact, there's a correlation between the material's density and its thermal conductivity. So less dense materials such as foams and fleeces are less able to conduct heat than denser materials like bricks or concrete. Bricks, for example, have a thermal conductivity of 0.77 watts per metre Kelvin, while our space-therm aerogel insulation is far lower at 0.015 watts per metre Kelvin. Thermal conductivity, however, only looks at the basic material. It doesn't account for the thickness. To factor in the material thickness, we take thickness in metres and divide it by the thermal conductivity to give us the thermal resistance, or R value, in meters squared Kelvin per watt. The next step is to convert that into a value for an entire wall, for which we use the thermal transmittance or U value, which is the inverse of the sum of the other R values for the different layers in the construction. U values are quoted in watts per meter squared Kelvin. Where R values vary proportionally to thickness of materials, U values do not, so as we move to lower U values, we need to add exponentially more insulation to improve them further. As an example, the limiting fabric parameter, more commonly referred to as the backstop or worst permissible U value for a wall given in approved document L for England and Wales, is 0.3, and the recommended worst case for a passive house is 0.015. The best practice passive house value is considerably lower at 0.06. In practice, compliance with either standard is more complex than achieving a simple maximum U value, but roughly speaking, the worst case U value for a passive house would be considered pretty good under national building regulations. The next principle is thermal bridge-free design. A thermal bridge occurs either where a material of higher thermal conductivity intersects a less conductive material, or where building elements join, such as at floor zones or corners. Thermal bridges have two principal negative effects. Firstly, they increase the overall heat loss by providing an easier pathway for heat to escape, and secondly, they create cold spots internally. Condensation and mould growth can occur in these areas, which has a detrimental effect on the indoor environment. The first of these, typically where structural elements like studs in a timber frame wall intersect the insulation, is accounted for via an adjustment in the U value calculation. This takes the thermal conductivity and proportional area of the bridges and adjusts the U value accordingly. If we consider a 140 mm thick panel of rigid foam insulation, if we use this in a typical timber frame wall, the U value then adjusted to account for cold bridging at the timber stud will work out to around 0.22. On the other hand, if we eliminated this cold bridging but used the same thickness of insulation in, for example, a structural insulated panel system, the U value drops to 0.15, purely due to the lack of repeating thermal bridges at the studs. Thermal bridging at corners and junctions is accounted for using an additional value for linear thermal bridging, known as a psi value. But in most cases, these are addressed using standardised pre-assessed details to limit heat loss. The easiest way to visualise the way thermal bridge-free design works in practice is to simply imagine drawing a pencil line around a cross-section of the entire heated envelope of the building. If that can be done without touching anything other than insulation, the design is free from thermal bridges. Because of the adverse effect that thermal bridging has on both the U value of individual elements and the overall energy performance, whether assessed via PHPP or SAP, reducing cold bridging in low-energy building is a matter not just of principle, but also of practicality. Getting U values anywhere close to passive houses' best practice performance levels without restricting thermal bridging is virtually impossible. But even in cases where designers are aiming for lower standards, the benefits regarding limiting localised condensation are clear. Whatever the assessment criteria, high-performance insulation systems like the Spacetherm Aerogel have a very important role to play in minimising thermal bridging by allowing the thermal resistance to be maximised at any given point. In locations such as window reveals and door openings, it can be difficult to maintain a similar level of insulation to that found over the main sections of a wall, leading to these areas being relatively cold. In extreme cases, this can cause the temperature to drop to the point where condensation may occur in these areas, and as fabric insulation levels increase, so does the importance of continuity and uniformity. Systems such as Spacetherm, which provide high thermal resistances in minimal thickness, allow for a more uniform envelope of thermal insulation performance, with the localised drop in R values around complex features minimised. The fire-rated Spacetherm Slentex A2 system also allows this continuity to be maintained where reduced combustibility is required, offering significantly higher performance per unit of thickness than conventional fire-rated insulation, such as mineral fibre. Fibrous insulation quilts typically have a thermal conductivity in the range of 0.035 to 0.44, which the Spacetherm is 0.015 to 0.19, meaning like-for-like performance can be achieved in less than half the thickness. While big thicknesses of insulation are expected and accounted for in passive and low-energy projects, it's not always possible to maintain such thickness over every part of the structure. Spacetherm can allow this uniformity to be achieved, and being of comparable permeability to fibre quilt to be achieved without compromising moisture movement. Spacetherm can be supplied in a variety of laminated board systems to suit most applications, as well as in self-adhering cold bridge strips for direct bonding to structural elements such as steelwork. This need to create uniformity of insulating value and prevent cold spots is also an important aspect to consider when specifying the windows in low-energy and passive projects. Passive and low-energy homes must pay particular attention to the specification of windows used, as poorly insulating windows can not only affect the overall heat loss, but, as with cold bridges, can also create cold spots and cold radiation. This phenomenon occurs where the influence of a cold surface can be felt nearby, often leading to a perception that a space is colder than it really is. Even by using multiple layers and glazing, inert gas fills, and thermally reflective coatings, windows still typically fall a long way short of the performance of the rest of the building envelope, with the passive house specifications calling for windows with a U value of 0.8 or less, significantly above the opaque elements. Windows are also important to provide heat into the building via solar gains, and for this reason passive houses in heating climates like the UK tend to position majority of glazing facing south in order to maximise this effect. This requirement to maximise collection of solar heat has to be carefully managed though, as highly insulated and airtight homes can be susceptible to overheating if this is not carefully assessed and managed. It's a common misconception that passive houses do not have opening windows, but in fact the specifications call for at least one opening window per room in the living spaces. Opening windows is among the most cost-effective and simple means of counteracting overheating, and is useful to prevent poor indoor air quality in exceptional circumstances such as large gatherings. That leads on to the next concept we need to consider, the airtightness of the structure. It's often said that airtight buildings can be like living in a plastic bag. However, this is a fundamental misunderstanding of what we mean by airtight buildings. Reducing air leakage simply means eliminating sources of air infiltration and exfiltration over which we have no control, drafts in other words. A good supply of fresh air is a critical component of healthy indoor living environments, and the passive house specification is designed to ensure this is facilitated by controlled and carefully managed ventilation systems, with considered impacts on energy performance. Uncontrolled air movement, on the other hand, should be reduced as much as possible. As we've covered already, the thickness of insulation layers increases exponentially with reductions in U value, and after a certain point this becomes both uneconomical and impractical, even in explicitly low-energy buildings. It's therefore very important that every other factor affecting energy performance is controlled and limited to minimise energy usage. In dwellings, there are two main drivers of air leakage: the internal stack pressure caused by the relative buoyancy or warm air and resultant convection, and external forces from the wind. Because warm air is less dense, it will rise upwards in a building and can leak out of any air pathways found at higher levels. Correspondingly, as this air rises, colder air must be drawn into the building lower down. As the warmer air will contain significantly more moisture, this outward air leakage can lead to condensation issues as the leaking air cools and deposits liquid water. The cooler air entering the structure lower down will lower the internal temperature in the building, necessitating energy input to maintain the temperature of the habitable space. Externally, the wind forces acting on the building will have similar effects, but inside of the pressure gradient working from bottom to top, it will be aligned to the wind direction. Cold air will be pushed in on the windward side where there is a positive pressure, and warm, moist air sucked out on the leeward side where the pressure is negative. Limiting this air movement is a critical part of the low-energy design, as even highly insulated building will have poor energy performance if the movement of air is not controlled. Both the building regulations and passive house standards therefore include pressure testing and minimum performance levels, but there are some important differences. The UK building regulations use a pressure test known as AP50, which is the volume of air in cubic metres that flows through the building fabric area in square metres in 1 hour when a reference pressure of 50 pascals is applied. This pressure can be applied in either direction, by pressurising or depressurising the building. The backstop value for this is 10 metres cubed per metre squared per hour in England, Wales and Northern Ireland. In Scotland and the Republic of Ireland, the preferred or reasonable limit is set at 7, and while it's theoretically possible to comply with a higher value, the necessary trade-offs will generally be unacceptable. Passive House expresses the air leakage differently, using a standard called N50, which is the air changes per hour through the building's internal heated volume, ACH, at the same 50 Pascal reference pressure. In the Passive House test, however, the pressure must be applied in both directions, pressurising and depressurising the building, and the two results averaged. The test equipment and physical procedure is largely the same for both AP50 and N50 tests. This means it's perfectly possible to run both simultaneously, but the way the final results are calculated is sufficiently different that conversion between the two values is not possible without access to the source data. The BRE's Passive House Airtightness Primer document, highly recommended as follow-up reading, gives a useful analogy to illustrate the difference in standards. A building with an air leakage rate roughly meeting the UK regulations limiting value of 10 metres cubed per square metre per hour AP50 will have gaps and cracks equivalent in area to 120 pence per square metre of floor area. In contrast, a passive house meeting the required 0.6 ACH N50 standard will have gaps equivalent in area to a 5 pence every 5 square metres of floor area. There are numerous ways of making buildings airtight, and finding the most appropriate method to apply to a given project is usually a matter of balancing a variety of competing requirements. Some strategies are easier than others, however. Some building materials, such as cast concrete, cross-laminated timber and structural insulated panels, have an inherent advantage when it comes to air leakage, as the basic materials involved have low air permeability. Others, like blockwork, are more permeable, so require additional measures to control air leakage. In all cases, though, junctions, services and the nature of the on-site assembly process still poses challenges to achieving a low air leakage rate, even when using the most impermeable base materials. The conventional solution to this is to seal the inside of the building using a vapour and air barrier membrane. The advantage of this approach is that the membrane fulfills a dual purpose, limiting both air leakage and vapour ingress into the structure. It's also something most contractors are familiar with. The downside to this approach is that the membrane integrity can be compromised by a variety of components and processes. Being internal, building services such as power, plumbing and network cabling must run through an internal air and vapour control layer. While this need not necessarily pose a problem, the nature of sites and trades, particularly in the UK, is such that VCL integrity cannot necessarily be depended on. Unless contractors of all disciplines are aware of the importance of this layer, suitably trained and equipped to avoid damaging it, and afforded sufficient time and space to undertake works in a manner that avoids puncturing this membrane, the scope for problems is limitless. Features like service voids, flexible pipe and cable gaskets, and sealed light fittings can all go some way to mitigating these risks, but these all increase costs and time demands, and aren't necessarily familiar to all contractors. For example, in Scandinavian countries, where low air leakage rates have long been standard practice, every plumber and electrician will be used to working carefully around air barriers. However, in the UK it's not uncommon for holes to be cut and drilled and work undertaken with no thought given to any knock-on effect on air movement. It can also take far longer on site to ensure every joint and penetration is adequately taped and sealed, often requiring different types of tapes for different circumstances. Acquiring all these tapes and sealants can also pose challenges if needed at short notice. Although this is changing gradually, with more contractors gaining Passive House certification, it's perhaps prudent for specifiers of low-energy buildings in the UK to look at alternative methods to mitigate these risks at the design stage. Moving the air barrier layer to the outside of the building, well away from any services and following trades, allows this to happen. Our wrap-type product is a self-adhered, vapour-permeable but airtight membrane suitable for use in both wall and roof applications. It's also certified by both the Passive House Institute and the BBA, so can be specified with confidence as an effective air barrier layer. On the outside of a building there are far fewer penetrations to seal, and those that are present tend to be larger and simpler to seal. Because the membrane is adhered fully to the substrate, it's also better able to resist damage. The self-adhesive backing also makes sealing laps and joints simple and fast, and the membrane itself can be fitted off-site, allowing it to provide protection during transportation as well as being used in the construction. In an off-site installation, the joints between adjacent panels or modules can be simply jointed on site using our split liner tape, which ensures fast and effective seals can be made in the air barrier. This also facilitates straightforward sealing of complex curves and forms, and means features such as floor zones and roof and wall junctions can be easily dealt with by simply wrapping the whole building in a single product. Once fitted, the building shell is then wind and watertight, so progress can be made on fitting out, and air pressure testing can be undertaken earlier in the build scheme, giving more flexibility on timings and potentially easier fixes to any problems that do arise. The primary benefit of the wrap-tight system is not so much that it reduces the overall air leakage rate, more that it makes achieving design air leakage rates far easier and more reliable. This in turn allows the benefits of airtight construction to be fully accounted for and integrated into holistic design, without fear of expensive and awkward remediations if targets are not met. The vapour permeability of wrap-tight also allows flexibility in insulation placement. It's perfectly possible, for example, to wrap a building with insulation between stud-work and wrap-tight, then fit additional external insulation layers to limit cold bridging without causing any moisture problems. That's not to say that we do not need to consider moisture control in this type of construction. An internal vapour and air barrier will also serve to limit the ingress of moisture vapour into the construction. So if we move the air barrier externally, we need to ensure that moisture is adequately controlled to prevent any condensation problems from arising. This can be achieved by either using insulation with a lower permeability to moisture vapour, such as most types of rigid foams, or by using a warm frame construction with insulation placed externally to limit temperature drops and ensure the dew point does not occur internally. Another option is to use a variable resistance membrane, such as our Procheck Adapt. This type of specialist membrane has been used in passive house constructions across Europe for many years, and when combined with an external air barrier membrane provides a comprehensive moisture and air movement control solution. The Procheck Adapt varies its resistance to moisture vapour according to the environmental conditions, becoming more resistant to vapour ingress in winter when condensation risks are highest, and then less permeable over the summer to facilitate drying out and allowing a more breathable construction. Used alongside wrap-tight, Procheck Adapt provides an additional level of protection against both air leakage and moisture issues. Any moisture that does make it into the construction as a result of damage during installation can easily dry out in either direction, which the movement of air is reliably restricted by the external air barrier. We also have the capability to run Wi-Fi-based condensation risk calculations. This covers a wide range of factors to ensure buildings are able to manage the interactions between heat, air and moisture movement. We've covered this in more detail already in our Membranes Explained, an Introduction to Building Physics webinars, and you can go back and review those on our website or YouTube channel if you'd like a bit more detail on that, or you can book a virtual meeting with one of our team if you'd prefer. The last of the passive principles is the use of ventilation with heat recovery, in which heat from the extracted airflow is recovered through a heat exchanger and fed back into the building via the incoming supply air. This improves the efficiency of the building by reducing heat wasted by the extract airflow, and such systems are generally required as part of the Passive House certification. Without heat recovery ventilation systems, it can be difficult to meet the space heating energy requirements. This requirement in the Passive House specification often leads to an incorrect assumption that all airtight buildings require mechanical ventilation. If designers are not working to the Passive House certification specification, then various other options for both ventilation and heat recovery are available. In fact, it's perfectly possible to have good indoor air quality at low air leakage levels with a fully passive ventilation system, provided this is designed into the building early enough. What's important here is ensuring the building as built meets what is specified, and here's where systems like wrap-tight are particularly useful. If you design the building heating and ventilation systems to operate with an air leakage rate of 3 meters cubed per square meter per hour, but when tested the building only achieves 7, then problems can arise as highly optimized heating systems may not be able to compensate for this shortfall. Conversely, if you design to 7 meters cubed per square meter per hour and actually achieve 3, then ventilation may not be able to supply sufficient fresh air to provide acceptable air quality. What's important is ensuring the building is constructed within its design specification, thus allowing all the building systems, active or passive, to perform as intended. A further possibility for the recovery of heat to lower the energy use in a home is to use heat pumps in the heating system. There are two primary types of heat pump, air source and ground source. Air-sourced heat pumps, or ASHPs, use heat-exchanging fluids and compressors to extract heat from the ambient external air supply and supply it into the interior of the home via a more or less conventional central heating or underfloor system. Ground-source heat pumps recover heat from collector loops buried underground. Fluid is circulated through these loops and picks up heat from the ground, which is then fed through a compressor and heat exchanger used to heat the home. Both of these systems commonly use a large water tank to act as a heat store, using the thermal mass of the water to retain heat energy until it is required by the heating and hot water systems within the house. Ensuring this heat store is well insulated is a critical part of ensuring these systems operate efficiently, and we have supplied the spacer insulation in blanket form for use in insulating a huge variety of tanks and vessels. Both ground and air-sourced heat pumps are designed to operate at lower temperatures than fossil fuel or electric heating systems, and this lower operating temperature works particularly well with underfloor heating systems. These lower temperatures, as well as the lower running costs, mean that these systems are typically designed to run continuously or almost continuously, and have less scope than traditional heating systems to boost their output and to meet additional demand. The better the energy performance of the dwelling they are fitted within, the more effective they will be. This makes these kind of systems a good fit for low-energy homes. The relative lack of spare heating output also reinforces the importance of predictable and reliable energy performance at the specification stage, as the only practical solution to an under-spec'd underfloor heating system is often the use of auxiliary electrical or solid fuel heating, which may not be a good fit with an energy-focused project. Although it's not Passive House certified, my own house used many of these principles to deliver an award-winning low-energy design by Scottish practice Alan Corfield Architects. Completed 2 years ago, it's a structural insulated panel home and adopts the passive principles of thermal bridge-free design and highly airtight construction, and also used a mechanical ventilation system with heat recovery to minimise energy requirements. If you've been following our webinar series, we discussed structural insulated panels last time, and this particular system is the Kingspan Tech panel system, supplied and erected by SIPS Scotland. These type of panels use a rigid urethane core with OSB facings, which limits cold bridging by having no structural penetrations through the insulation layers. OSB also delivers good air leakage performance, and this is boosted here by using both RapTight externally and our Reflectitherm Premier reflective vapour control layer on the inside. This reflective system not only lowers the U value of the wall with its 0.78 thermal resistance, but the adjacent service void helps minimise penetration through the VCL. This reduces the potential for moisture vapour ingress and further limits air movement. The Reflectitherm Premier, like the Procheck Adapt, features an integrated lap joint tape, helping facilitate a good quality installation. The use of systems and materials which simplify installation, along with experience and expertise of specialist contractors familiar with the use of SIP systems and delivery of low-energy focused projects, was key to delivering good results. So hopefully we've covered a lot of the basics today and given you a good overview of where to start with passive and low-energy designs. There really is a wealth of amazing resources out there, from BRE documentation to the Passive House Institute guidance, and we've barely scratched the surface of the factors that go into creating and delivering a successful low-energy home. We do have a team of technical experts across the country, so anyone involved in these kind of projects, simply get in touch and we can assist right throughout the process. So we'll now move on to the Q&A session. Good morning, everyone. Thank you very much for joining what is now our 10th webinar in this series we've been doing since the start of lockdown. So I'm not sure if I can still refer to them as lockdown webinars. I know in Scotland I can. We can't go anywhere still. So anyone that's lucky enough to be watching where lockdown is lifting slightly, we're not there yet, but hopefully we will catch up with you soon. As you know, we will try our best to answer all your questions. So I can see some coming through on the YouTube chat now, which is fantastic. So feel free to post any more you may have or email webinar@proctorgroup.com. Please don't email website@proctorgroup.com, or if you have, resend them to webinar.com, or you can DM us on Twitter @proctorgroup. All the information you need is on the webinar page on our website. So if you go to www.proctorgroup.com/webinar, you can download an information sample pack there, request a meeting, review your CAD drawings for your particular project. So we have a lot of things that you can do on that page now. You can also find there your personalised CPD certification. And after this, the Q&A session, we will be sending a follow-up email, which will have a link to all these different areas. And you can also find them in the YouTube feed. We love getting your feedback. There's also a short survey on there, so please complete it if you have time. I read all of it. And as a team, we take these comments on board and we try to use them to shape the future webinars. So if you can, please read it. I'm getting there. So 2 weeks today is our next webinar, which is the self-build process and considerations. We saw my house there, and so that will be featured in a bit more detail. Was the bane of my life for quite a short time. For those interested, it's pronounced Tickety-boo, so quite a different Scottish pronunciation there. We like to confuse the postie. So please join us if you can. Lastly, if you can give us a thumbs up or subscribe, it does really help us. So please feel free to do that. So last week we had a slight issue with the mic, so I'm just going to introduce people and ask you to say hello as I go, if that's okay. So some familiar faces, welcome back. So Callum, morning Callum.
Morning.
Great, okay. Callum's based in Crieff, which is about 45 minutes from the office. Lovely part of the world, and he is our technical advisor. Very savvy and with an architectural background, you know, very savvy on all things woofy, and a lot of technical experience, so he can help you with any questions you may have. Come on to Mark Lambourne, who is our business development manager. Morning, Mark.
Morning.
Great. So Mark's based in Derby, I believe, and has had a previous history with the Proctor Group, and came back to work for us last year, which we were very happy about. And again, many years in the construction sector. Adam Salt is our regional sales manager based near Bristol. Great, okay, we can hear you as well, Adam, fantastic. Welcome, Adam. Adam's got a background in the insulation sector, so brought another area of expertise to the business when he joined us some time ago. And last but not least, James Brackenreid-Johnson is based in Eastbourne. Morning, James.
How are we doing, all right?
Lovely, lovely. James has had a few days off this week and he's enjoyed the sun, like us Scots and others here. So James is our London specification manager. He covers the London area, but operating relatively nationally at the moment. So again, a lot of experience that can help you with any questions you may have. Okay, so I think that's it. I'm just going to come on straight away to some of the questions, guys. If you're coming through, as I said at the beginning, we will stay on and answer all the questions, but if you have somewhere to be, feel free to leave at any point, and you can watch a replay when the email comes out. Follow the link, and if you don't have time now, you can catch up with all the Q&A at a later time. But we hope you can hang on and stay with us. So I'll just come to Linda first. Mark, if I can, 1 second. Right, losing my paperwork here. So James McGregor, sorry, let's come to him first and I'll come back to Linda's. James has asked Mark, what about the VCL when using Raptite? Is that still required?
Yeah, morning everyone. There is no truth in the rumour that James was on the beach in Bournemouth for a couple of days this week, so I'll get out that way. Yes, with regard to the use of VCLs with Raptite, that really depends on the placement, the type, and the thickness of the insulation. So it probably lends itself more towards, I guess, the high-rise residential projects that we're involved with, where the insulation is placed externally on the sheathing board and also between the SFS. On some of the other projects, it's likely that we will also need to use a VCL, and Callum can certainly use the Buffy analysis and hygrothermal assessment to determine whether that's the case. But it's more likely that what we're looking to do is achieve the air tightness line with the Raptite and then use a VCL internally. And what you might want to consider is the use of the Procheck Adapt, this variable membrane, for the moisture management side. So that was touched upon within the webinar. Really, there's no simple yes or no answer. We'll look at each project on its own merits, and as I say, Callum can run the necessary software, etc., to determine if it's required or not.
Okay, thank you, Mark. So that does actually link in with Linda's question, which I was going to ask first. But so Adam, if I can come to you on this one, please. Linda's been looking at some of our vapor control products. How does the Procheck Adapt differ from a standard vapor control layer, and how does it actually work?
Okay, yeah, morning everyone. So the Procheck Adapt, so that's a vapor control layer that has a variable permeability. Now what that means is to the changes in the humidity levels by becoming more resistant in the winter and more permeable in the summer. So when it's hot, the building fabric is allowed to dry out more effectively, and in those winter colder months, the membrane is protecting that building fabric from any damaging moisture levels. I think my technical director, Ian Fairlington, always refers it to as quite similar to our skin. The pores open when it's hot, and then they close during the colder months. So it works in a very similar process if you're struggling to get your head around it. Now, because of this, the Adapt has a wide range of SD values, which guarantees performance throughout the damaging climatic conditions. So to answer the question, Procheck Adapt differs because the Adapt is a dynamic VCL because of its changes of vapor permeability, whereas a normal vapor control layer, however, is static between the two. So that's how that one works, really.
Okay, that's lovely. Thank you very much. Joe has asked Callum.
Yeah.
Sorry, Adam, there's a bit of delay there. Thank you for that. Callum, when come to you, Joe has asked how much thermal bridging is required.
Okay, so the approved document L requires that you make reasonable consideration of thermal bridging. Ideally, for a SAP or SBM calculation, these should be calculated things. So you would take the psi value of the linear thermal bridge. Passive house requirements go a bit further than that. They require thermal bridges to have a psi value of less than 0.01 watts per meter Kelvin. But they do state that with increased performance at the thermal bridge, you can actually get negative psi values. So that's where it's better than the adjacent construction. Typically, we would recommend maybe 10 to 20 millimeters of our space time to show reasonable provision of a broken thermal bridge.
Okay, great. That's actually a product we used in this house build. So this is the kitchen area. We have a sunken living room. So we actually use the Space Therm product on the thermal bridge between the kitchen area and the sunken area in the living room, which was quite a unique solution in that sense. Cal, maybe you can help with Peter's question as well. Is the condensation risk software linked to NVHR system to regulate flow rates?
Okay. So the condensation risk analysis is a calculation that's done before the construction. It's not a live thing that feeds into the system. I believe there are some NVHR systems that can, well, most will measure and react accordingly to the conditions of the room. I don't believe it's based on the output of the condensation risk analysis.
Okay, so not linked. But that's something, again, Peter, that if you want to email us with more specific details, we might not have the exact answer, but we might have some within our network. Either we know that, supplies NVHR that we could link with and put you in touch with to have a discussion on that. James, another question here from Joseph. Do we just have to insulate externally or internally?
Great question. Just to say thank you very much to Mike Stripling for his comment regarding my tan. My apologies in regards to that. Yes, I mean, in regards to insulating externally or internally, it's project specific. Obviously, from the point of view of having an aesthetic facade, you'd want to insulate internally. Generically speaking, if you're looking at a terrace property or mid-terrace property, then what you'd be looking at is insulating down the flank of the building externally and insulating internally on the facade. But what I'd stipulate is to be careful of the junction between that facade and the flank wall to make sure that there's no cold bridging between that corner element there. And then on the back of the building as well, because generically speaking, what you'd be looking at is having a kitchen in the back of the property, insulating externally as well, because you'll get a lot of the penetrations. You'll have to have obviously the reinforcement in that internal wall to hang the kitchen units on. So making sure that external facade has the insulation as opposed to internal. Again, is on a very bespoke basis. Each project will have to be dealt with differently. So apart from dealing with the cold bridging, it's worth looking at the fact that you're not going to be causing any condensation issues by under-insulating the areas that you're looking at, because you can, if there's a certain percentage that is insulated, but it's not enough of that one area, then what you can do is compound the problems. Generically speaking, you're going to be looking at a window reveal that these problems are where these problems compound. So utilising a thinner, more efficient material in those window reveals as opposed to just leaving them bare is the best way to go.
Okay, that's great. Thank you, James. I'm just going to put this one out here. Roofing Today has asked, and again, I'll ask anyone if anyone's aware of the answer to this. I personally don't know. I haven't built a passive house. And obviously we are material manufacturers, so we're not involved in the actual construction of the passive houses. However, our products obviously are passive house. Some of our products are passive house certified. Are any of you guys aware of how easy it is to find a suitably qualified contractor if you have any repairs or remediations to do on a passive house project? No, no one answering immediately is saying that maybe we
no, but I think we would know people that would potentially be able to assist with that. You know, we have a great database and connections with relationships with people. So really get in contact, maybe have a meeting, we'll discuss your project and we'll assist with you there, I think would be the answer on that one.
That's great. Thanks, Adam. So yeah, again, if you're an individual or the magazine wants to email us in to webinar@proctorgroup.com, we will put you in touch with someone who can help you. Another sort of generic one, Cal, you may know a little bit about this. Air source heat pumps. Do we believe they're currently worth the investment, or is the technology not quite there? Obviously not our area of expertise. Do you have any opinions you want to share on that?
I know that they are constantly improving, as everything in the industry is. I would say that yes, at the moment they are worth the investment.
Okay. Good.
I would say yes.
And definitely worth.
Just to add to that one, if I can, it's from a new build perspective, the investment of heat recovery systems is definitely viable, but in regards to a retrofit standard, it tends to be more cost effective not to have them in there. If you're looking at sort of solar thermal or PV panels from a retrospective point of view, they are becoming more and more viable economically to be done retrofit. But obviously from a new build perspective, it's definitely the way forward because it's an automatic win straight away with the power bills.
Okay, good. Just a few coming into the webinar address that aren't on the feed, and I'll come back to that. James, while we've got you, Lewis has asked, what is the best way to deal with cold bridging?
Cold bridging is something that's haunted people for years, architects and contractors alike, through the different contracts that have occurred over the last few decades. Obviously, predominantly you're looking at design and build contracts in this day and age, which the architect gets to sort of design the through wall systems, but generically leaves the detailing, i.e. the cold bridging elements, those junctions, to the contractor to utilize either robust detailing or one of their own approved details and have them checked on site. It's not a case of, there's never a simple answer. From a structural point of view, the rule of thumb has always been to utilize a 25mm rigid insulation, or to pack in as much mineral wool into that boxing detail or around that steel work and then box that in. On a roofing point of view, then people would generally go for a 50mm board in order to negate that cold bridge. With obviously such products that we have, like the Space Therm product, which has a thickness of 10mm. We've got the market leading lambda of 0.015 for our standard Space Therm blanket and 0.019 watts per square meter Kelvin for our Slentex A2 version. And obviously, when you're looking at your PIRs, which are sort of circa 0.022 watts per square meter Kelvin, your phenolics of 0.020 watts per square meter Kelvin, our product is a better performing product in regards to that situation. So therefore, putting the product into that cold bridging element and making a finer detail of it, instead of packing it full of mineral wool, instead of sort of getting a thick foil-faced board over your cold bridging element, which indeed, due to the foil facing, may actually create a condensation risk because of that foil facing in that environment. Obviously, we can't do calculations on cold bridging, so all we can do is merely advise that you utilise an insulant, and from a space therm point of view, utilising the 10 mil space therm to encapsulate the areas or cover the areas where you've got your cold bridging is the minimalist amount of insulation you can utilise. Again, it doesn't have foil facing on. It's a vapor permeable product, so you won't be causing any condensation risk within that area, and you'll be negating the cold bridge.
Okay, great. Thank you, James. Callum, there's a question here about the PHPP calculation package for Passive House Standard. Do we have any additional material that we could share regarding the principles and how to use it? Is that something you can tell us a little bit more about?
Not really. So for the most part, the PHPP is essentially a spreadsheet that you input the various values into. Okay. It's not really one that I've used myself, so I'm not overly familiar with it. But from what I've seen, it is fairly easy to use.
Okay, thank you very much, Callum. Thank you. Just going to Mike's comment about your tan, James. I must agree. We're all very jealous. You picked a good week. Mark, on the other hand, had limited days off since lockdown, and every day it has rained. So no one take a day's holiday the same as Mark. Poor guy. Oh dear. So coming on to you, Mark, actually. Simon has asked, why do low energy homes need to be airtight?
Why do they need to be airtight? Well, really you're looking to improve the airtightness of the structure to improve the energy efficiency of the building. So if you're looking at the way we traditionally look to improve the energy efficiency of a building, would be to increase the levels of insulation that's required. And that's really been driven, I guess, by the insulation manufacturers, where they'll encourage you to put more and more insulation into the structure. And that's the way that you achieve more energy efficient building and structure, whether it be walls, floors or roofs. What you can do is obviously improve the air tightness of the structure. And certainly within SAT calculations, for example, if you were to take the air tightness levels down, so by using a membrane at less than 1 millimeter thick, then you can improve the air tightness of the structure, reduce the amount of stop this leaky building syndrome, and use sensible levels of insulation. So insulation is not necessarily the right way to go. Use it correctly, but have this balance between air tightness and also sensible levels of insulation to allow us to build to more energy efficient buildings.
Okay. And a question that's been asked on the feed from Robert Mark as well. I think this also links with airtightness. So he's asking about the gap in training competence between the Scandinavian and UK tradesmen in terms of closing the gap between designed and as-built performance. So do we think there's a bit of a shortfall there? And I guess it's something we are seeing more education in terms of how to achieve airtightness in the UK. Okay, the regulations aren't quite where Scandinavia is.
Yes.
Is there anything you want to add comment to?
No, really, I think it's as with anything, we issue with all our products detailed installation guides. And to try and encourage the use of those, there's lots of very good graphics on there, simple detailing step by step. But it's a great British tradition of just screwing that up, throwing it away, and installing products how you think they should be installed. So we sort of encourage that people look at those installation guides, but to sort of back that up, we know that doesn't really happen. So we sort of, wherever possible, will go out to site or at the current time use Zoom meetings, etc., and video clips and that type of thing to sort of explain the importance of these products and how they should be installed correctly. So it's well worthwhile spending half hour or so with the guys to let them fully understand, talk them through the installation guide, and that can save a lot of headaches in future.
Yeah, absolutely. And I think, as we saw in the presentation earlier, the difference between having the airtightness layer externally of the envelope of the building and relying on that as your airtight layer can be much easier to achieve and less labor and time consuming using a product like WrapTight in comparison to, you know, the raft of internal products that you may use to make the airtight layer internally. So certainly the project studies we've done, and we can share this with you know, the individuals that are watching if you like. We've done trial projects looking at the time and airtightness results when we've done a dwelling with internal airtight measures, you know, tapes, everything all around the different junctions and ceiling versus WrapTight. And we actually tested that project. We tested both dwellings before a vapor controller was installed on the WrapTight project, and it achieved you know, below 1 airtightness tests without any vapor controller internally, which was a fantastic result. Whereas the other one, they had to do a lot of remediation. The smoke test showed a lot of areas that they had to change. So it really was a great case study. So again, that's something that we can share with you if you are interested. Okay, let's have a look. So question here from Boris. If there's already a thermal bridge at point of the structural timber studs of an existing build, what is the remedy? Insulate by wrapping around on the inside? Callum, is that perhaps a good one for you?
So timber's not as bad as a thermal bridge as, for example, steel. It has a thermal conductivity of about 0.13 compared to steel, which is usually about 50. So often people do just leave it as a thermal bridge. It's not as bad as it could be. You can put a thermal lining on the inside, so you could have a strip of our space therm cold bridge strip on the inside of the stud, for example. You could also improve the entire wall by using one of our space therm laminates across the entire face of it.
Okay, thank you, Callum. Adam, I haven't spoken to you for a while. So Joe has asked, in my current house, I have an uninsulated timber floor. What improvements do you recommend?
Right, okay. Firstly, I think Mark's got some days off next week, so avoid having any days off next week. But no, so an uninsulated timber floor. Okay, so these days we talk about, well, I think even in the presentation, we always mention airtightness, but the old terminology for it was drafts. It's very common in these uninsulated timber floors to have a lot of those air leakage draft areas. In fact, even in some older properties, you'll find under the skirting boards, there'll be newspaper where people have tried to block that air leakage draft area and eliminate it using the newspaper. Some people can also use tapes. The issue with a lot of the tapes out there is they're likely to be impermeable, so that increases the chance of getting condensation there. Now we have a WrapTight tape, which is airtight and breathable, so you'll get the benefits there of putting that down and not getting a condensation risk. You've also, compared to paper, you won't have to look at the laps because it's just a tape you lay down. So that's something you could do just going around the sort of outside of the floor. But then if we look at the whole surface, there's sort of two options. One, you can lift up the floorboards, lay a membrane down, I think even some chicken wire, and then add some insulation. That will obviously improve the thermal performance. Or a simpler method, I believe, would be to lay our space for multi down and then use, again, the WrapTight tape to seal all the joints. You could potentially lay the WrapTight membrane down over the floor. That will obviously reduce the drafts as well, but you won't get the added thermal performance from the space firm multi. So that's an option. And then potentially you can also continue that method up to the solid walls. If you have solid walls, the WrapTight would obviously depend on the surface it's going on. So each project is different. Please obviously get in contact and check with us first. But yeah, again, WrapTight on the walls, you can then batten that out and place the multi on top. Or we could look at space firm systems to go straight onto those walls and protect any of those drafts as well. So yeah.
Good. Okay. Thank you very much, Adam. Sorry, I'm getting lost with the questions. I'm hoping I'm not going to miss any here. Okay, one from Richard. Can you fix a rain screen cladding system direct to the Raptite, or are there other measures required to seal fixings? So Mark or James, that's kind of your area. Mark, do you want to?
Yeah, by all means. Yeah, we've got some very good independent sort of test data from Wintec, for example, where we've done some testing on a typical high-rise type construction. So this is an SFS type system, a sheathing board, and then Raptite adhered over the face of that. Then there's a series of fixings that have penetrated through, so various rail systems, etc. And then we've done the Wintec testing to understand what effect, if any, there was on the airtightness results. And the results came back very, very impressive, actually. There was little differential between testing it prior to and then after all the fixings were in place. So again, that's information that we can share, and if you want to get in contact, we can talk you through that and look at possibly any specific detailing you may have on the project.
Okay, good, thank you. Cam, if I can come to you, question from Sean. If using DMEV as opposed to Passive House for a new build, what Proctor products would you suggest for achieving an air test between 3 and 5?
Okay, so DMEV is decentralized mechanical extract ventilation. So that's when the extractor isn't located in the same place as the building, it's a bit distant. With that system, we would recommend, well, you can use any of our AirTech products, such as Raptite or a vapor control layer internally. Really, all that you're looking to do there is make sure that the penetrations around that DMEV unit is sealed properly. So that could be done using our Raptite tape, for example, or any of our tapes on the inside through the vapor control layer, like our reflective foil.
Lovely. Thank you very much indeed. Just a quick one from Mike, who's asked, is Procheck self-adhesive like Raptite? I'll just answer that quickly. Well, it's not completely self-adhesive like the Raptite is full coverage, but it does have integrated strips. So obviously, for sealing the Adapt, it makes it very usable on site from a labour point of view, and you then have that airtight seal at the labs of the product. Okay, I'm going to just catch up some of the email ones. I think there's 3 or 4 here. So James, we haven't spoken to you for a little while, from Claire. Claire has a historic detached building which has numerous curved walls and an aesthetic facade. Can I send you some drawings? Well, yes, Claire, you can. So how would she insulate, she's asked?
Okay, the way to insulate would be internally, obviously, if you've got the aesthetic facade, especially on a historic building. In regards to curved walls, obviously utilising a rigid board wouldn't be plausible because obviously the nature of the board. Mineral wool could be utilised, however, it'd be very bulky. And obviously from a historic point of view, the usable space internally is generically a lot smaller than a modern day property. So therefore, obviously utilising a bulky insulant will obviously encroach too much on that internal usable space. So from our point of view, we'd say yes, insulate internally, and you can utilise our Space Therm product, or indeed, depending upon the substrate that it's going on to, you can either utilise our Wrap Therm product, which will enable you to, one, keep that breathability going, but two, insulate as well at the same time. But from a standard point of view, if you're utilising the Space Therm blanket, the nature of the blanket itself, I do have samples here today, like my colleague Mark normally has, but today I have them. So basically the product itself is very robust and very flexible. So where you've got a curved wall, or, so it's curving down the stairs on that wall, or a ceiling or anything on that sort of line, then you can utilise that blanket. If I relate to a project that we've worked on, it's a 16th century property that had been worked on, and basically they wanted to retain and they wanted to keep chestnut laths and utilise lime plast afterwards. So what we did was we took the existing substrate off, back to the stud-work, back to the rafters, and then mechanically fixed the Space Therm with a mesh over the top, and then had the laths over the top of that. and then the lime render was put onto that, and it all bonded very well. But you've still got that vapor drive, because historically speaking as well, the wall build-ups from historic buildings are a lot more permeable than what they are in today's way. So therefore, having that vapor permeable product to allow that vapor drive, egress and ingress still through the product is a good way of keeping that building breathing.
Okay, good. Thank you, James. Callum, two kind of ones here around certification and passive house, if I can come to you. One from Rob, can passive house certification be achieved for low energy retrofit projects? And the second one, in fact, if you want to answer that one first, I won't overload you with two. So
yes, passive house certification can be used for low energy retrofit projects. They also have a second standard called Enerfit, which has slightly reduced requirements. So that's easier to get for a retrofit project.
What's the main difference between Enerfit and passive house? Just performance.
The main difference is that where passive house requires an air tightness of 0.6 air changes per hour, Enerfit allows up to 1, but you have to consider things like thermal bridges a lot more.
Okay, good. Well, we did have another question about air tightness levels from Mike, just generally what level of air tightness is expected. So you kind of answered that there. Is there anything you want to add about the air tightness, or are you quite happy with that?
Yes, so as you said in the webinar, the limit for air tightness in the UK is 10 meters cubed per meter squared per hour at 50 pascals. A lot of older buildings aren't built to even that standard, which is why they're incredibly leaky. Scotland reduces that to about 7, and most buildings in the UK are built to about 5 nowadays. Below 3, you would need to introduce a mechanical ventilation unit. Although recent research from the Passive House Trust has shown that MVHR system would work well in any air tightness limit. It's not detrimental to construction above 3. And obviously, the more airtight you have the building, the better it will perform.
And the other question I was going to ask was, I'm not sure if you know much about this, are you aware of the Future Home Standard 2025, and how do passive house standards compare to that?
I'm not as familiar with the standard. I wouldn't be able to do a comparison, but if you send us an email, we'd be able to compare them for you.
Okay, lovely. Thank you very much. Adam, I can come back to you, please. John has asked, well, he says, I live in a 1930s property. Should I think about improving the performance of the property? And if so, how do I do that?
Right, okay. We get a lot of questions about sort of older properties. And I think that's probably because 30% of Europe's building stock is built prior to 1945. And the UK, within Europe, has the oldest housing, with 38% built prior to 1946. Now, all of these properties are trying to cope with the modern day ways of living, the heating systems that we these days seem to turn on whenever we like, without even thinking about it. Now, heating these properties come with 2 main issues. The first one being it's expensive to heat because the lack of insulation. And secondly, we've got heating these properties actually result in a large CO2 emission because a lot more heating has been used and it goes straight out. I think heating is one of the biggest contributors to CO2 emissions in the whole of Europe. So yes, I would say there's actual big need to be improving the performance of not only this property but all the properties. Now, by insulating, we're obviously going to reduce the amount of CO2 emissions being produced and make it cheaper. With a new build, I think as James might have mentioned before, that would be quite simple to upgrade. It's a design, we've got no existing structure to look at, so we don't have many thermal bridging issues. But when we're looking at existing properties, we now have a number of challenges. From a design point of view, it's easy to go external, there'll be less thermal bridges, but a lot of those have those architectural details that we don't obviously want to cover up. Properties in Bath, for example, with all those old Bath stones. So we then have to look at internal, which then leads us to a load of thermal bridging issues, which makes it a bit more complex. Also, people put insulations onto their walls internally, and what that's actually doing is making the wall a lot colder, and that means they're more likely increasing the chance of condensation because there's no warm air passing through. We've also then got the other effect of freeze-thaw, where the wind-driven rain is being caught up within the construction, and then over the colder months freezing and starting to crumble in the outer surface. So what we then say is, well, we need an impermeable insulation to resolve that, to allow that warm air to pass through, keep that construction a lot warmer. But the issues with using impermeable insulations is they tend to have a much higher thermal conductivity. Therefore, we're looking at greater thicknesses. We've then got bigger loss of space in the floor. So it's very challenging into design. But with obviously our space foam range, it's not only breathable, but it has a thermal performance of 0.015, which is better than most sort of commodity impermeable solutions. And that way we can reduce the thickness loss and give you a much more improved thermal performance. And also, so yeah, I'd recommend space foam for that project.
Okay, that's great. Thank you very much, Adam. Just a couple of questions left now, so we'll just be wrapping up shortly, not for the weekend unfortunately, but for the webinar. I love this question. I was on a different seminar about passive house at the start of lockdown actually, and someone asked this. So Jamal has asked Callum, is it true that you need to keep your windows closed when living in a passive house?
Not at all. So obviously the airtightness test is carried out when the windows are closed. It's designed to account for uncontrolled air leakage. A passive house a passive house is designed so that you are thermally comfortable in the house with the windows closed, but you certainly can open the windows if you want a fresh breeze or to hear the birds singing, for example.
Very good. Yeah, it's a common misconception that we hear a lot about. And I think we've answered everything else, or some of the questions kind of overlap. So I feel like we've answered everything on the YouTube feed. So again, if there's anything that you feel like your question's got unanswered or you need more information, please email webinar@proctorgroup.com. So I'll just go on to the very last question, which was emailed to us from Jill. How can we achieve good airtightness in practice? Mark, could you answer that one, please?
Yeah, I think we sort of covered it in some of the previous questions. Really down to attention to detail, a bit of common sense. I know that's a dwindling attribute these days, but a bit of common sense and really compliance with installation guides, as I said earlier. And please, make sure that you read them. As I said earlier, on-site installation training will be available actually when we're back up and running as normal, but we're doing that over Zoom meetings. We've actually got contractors, as James and I did only last week, where the guy is walking around with his phone showing us issues and problems he's got, and we were talking those through, and that helped to rectify everything. But really, I guess good practice, as with any self-adhered membrane or tape, so if you're using the RAPTIGHT, for example, good air tightness lines are achieved by ensuring surfaces are really sort of dry and dust-free. And when you're applying these membranes or tapes, make sure you use firm pressure, so perhaps using a roller, and particularly around window openings, etc., use a smaller roller and make sure you apply enough pressure to make sure there's a good bond there. Another great British tradition that we do is if we're putting round pipes through various substrates, we tend to do big square holes. So try and think about that. Look at how we detail things differently. Make sure that we seal around any of those penetrations. And again, we can do that with RAPTIGHT tape or with our liquid flashing. So make sure that those are detailed correctly, and make sure that other trades really understand the importance of these membranes, whether they be internally or externally, and perhaps do a little bit of a teaching to those guys to make them fully aware of the issues and problems if they put a Stanley knife through an internal VCL to try and run an electrical cable or whatever it may be, because these things very quickly get covered up, and then the problems don't sort of present themselves until a few months or years down the line. So other things to consider really is perhaps when you're installing air tightness membranes, particularly with low energy homes or the passive house standard, perhaps use stage air tightness testing. So as soon as the air barrier is in place and the windows are sealed, etc., you might want to run an air tightness test at that point to understand what you're achieving, and then install all the necessary services and kitchens and appliances and that type of thing, and perhaps run another air test then. And then see if necessary, do any remediation works, and then run a final air test. So you could find you actually got 3 different air tests involved if you're driving down to very, very low air tightness standards. But actually, if you've done, as I say, the attention to detail, applied a bit of the old common sense and you know, best practice, that may or may not be necessary.
Great, thank you very much. So I think we've come to the end of all our questions. So I just want to thank all the attendees that have come to this week's webinar, and also thank you for your thank yous and the comments on the YouTube feed. Really nice to see those, and it's great to share them with the team. So not all the team that have worked on the webinar are here, of course. So thank you to you guys for coming and answering the questions. I know it's not easy when you're under pressure, so you all do great. So thank you very much, and thank you to our marketing team who are putting these webinars together. They're proving their weight in gold at the moment. Well, not that they don't always, but doing a really great job for the Proctor Group on what they're providing. So next week, so 2 weeks today, we have our 11th webinar, which will be the self-build process and considerations. So we saw my house featured here as a very brief case study. So that was a time lapse of the structural kit going up. So we'll be going a bit more into detail in that. And for me, it was a very interesting process. Being in the construction sector and at the other side of the build process, so as in not acting as the manufacturer and provider of the products, finding out how it actually works, how it goes together, how the different products perform, and dealing with all the different trades and manufacturers. So it was quite an interesting journey, and we were selective with who we told in terms of when we were purchasing materials that I was in the sector and who I wasn't. So it's interesting some of the things you get told when they don't think you know anything. So it was a real learning curve, and again, just that whole process around information sharing with self-builders. So if you are interested in self-build, please join. If you're not, and you're just interested in general regulations and product and applications, there's still going to be a lot of interesting stuff. So we'll hopefully go a little bit more into depth in that particular case study and the wider general types of building and how you can achieve what it is you want to achieve in self-build. So we will be sending out an email after this. It will also have a link to a replay, so please feel free to forward it on to your colleagues or anyone who you may find it of interest. You will be able to get a personalised CPD, which you can download on our page, www.proctergroup.com/webinar. And that page also gives you a lot of other facilities. You can download an information pack or request information on this particular webinar or even our prior webinars. So we have had 9 before this, a lot of them very informative on different topics. So please feel free to peruse any of the previous webinars and ask for information on those. You can also request a meeting or an online CPD seminar for your architectural practice. I think Mark had mentioned, you've been on site virtually recently, and I've been really surprised with the amount of meetings and different types of support we're providing to people remotely. So we don't know the restrictions of lockdown, but we know them in Scotland at the moment, and how long that will go on for, and what our working day will look like in the coming months. So please use please use us for support remotely during this time. Yeah, that's about it. So the registrations for the webinar in 2 weeks is now open. So please go and register if you're coming back. If you can give us a thumbs up or subscribe to our channel, we like it. We have a little competition in-house to see how many extra thumbs ups or subscribes we'll get. So we have a little sweepy on. So if you can, we'd appreciate it. And thank you very much. We hope to see you in 2 weeks' time. Enjoy your weekend.
Bye.
Thank you very much.
Okay, bye.